Hi everyone, welcome back. We're now starting chapter 15, which focuses on integration of multivariable functions. So before we get into multivariable functions, let's take a peek back to what we know about integration and the area problem for functions of a single variable. So what we're interested in here is we want to calculate the area of the region that lies above the line segment 0, 2 and below the parabola. So we have a parabola that looks something like this, crosses at x equals 4, that's y equals 16 minus x squared, and we are interested in the line segment between 0 to 2 and finding the area underneath the parabola and above the x-axis. So that's the area we want to find. The way we did this in Calculus 2 is to integrate over all of the lengths of these line segments. So I've got an arbitrary line segment here at x, but we integrate over the lengths of all of these line segments as x goes from 0 to 2. So in order to find the area, what we did was we integrated from 0 to 2 the lengths of all of these line segments. In this case, they're just given by the y value, dx. Or in other words, we're integrating from 0 to 2 of 16 minus x squared dx. So I like to think about it in terms of we are integrating over the lengths of these line segments because that helps us figure out how to set up integrals for other problems as well. So the way I'm thinking about this is I've got this line segment and I'm just letting it sweep from x equals 0 all the way out to x equals 2. I have an expression for the length of all of these line segments and I just integrate over their lengths. And their lengths are 16 minus x squared. You can think that this is essentially what we did when we did things like finding the volume of a solid of revolution. If we did the washer or the disk method, we integrated over all of the disks, the area of the disks that swept out the region. Or if we used the shell method, we integrated over all of the surface areas of the shells that swept out the region. So it wasn't just we were integrating over line segments, we were integrating over an object of one dimension less than the object we're trying to find the area, volume, etc. of. And then we integrate over all of those objects of one dimension less to fill out the object of one dimension higher. Okay, so in this case, we've set up our integral and we can go ahead and calculate it. The way we calculated integrals in Calculus 2 was through antidifferentiation. So we found the antiderivative. And then we evaluated at the endpoints, took their difference. So that would have been 32 minus 8 thirds, and then minus 0. So maybe I'll add that in, minus the expression we get when we plug 0 in. Or 32 minus 8 thirds, that's 96 minus 8 thirds, or 88 thirds. So there's our final result. Now the key takeaway here is that how did we find the area? We integrated over all of the lengths of the line segments that swept it out. That's the idea that we're going to use moving forward. Okay, so what's the problem now that we're going to focus on in Calculus 3? Well, let's calculate the volume of the solid that lies above this region in the plane, so namely the square, 0, 2, 0, 2, and below the elliptic paraboloid. So that's now what we're interested in, finding the volume of that region. Let's go to a demo. So this is the region that we are interested in finding the volume of. So we can see we're sitting over that region in the plane that goes from, x goes from 0 to 2, maybe I'll hold it this way, x goes from 0 to 2, y goes from 0 to 2. And we want to find the volume of the region above it. Now this isn't a rectangular box. If it was, then that would be nice because we could find the volume rather easily. Length times width times height. But instead we don't have a rectangular box, we have this curved top. So how do we deal with that? Well, I'm going to switch to a different visual. So here we've got our same surface. There's the region that we're interested in finding the volume underneath the surface over that region. But what I've done is I've capped off the top by a flat top because I can work out the volume of this box the volume of this box would be an overestimate for the volume underneath the surface. The height of this box, well, I just used that sample point at the top there, which is when x is 0, y is 0, I plug that into the function and I get the value of 16. So now I've got a box of height 16 and the length and the width are 2 and 2, so I can work out the volume of this box and get an overestimate. But I can continue doing this. I can use more and more rectangles. So in this case, I've split up the interval from 0 to 2 along the x-axis into 10 subintervals, and similarly along the y-axis. That's created 10 squares, and I'll refer to them as rectangles because in general they're not going to be squares. So I've got 10 rectangles along, or 100 rectangles, 10 by an array of 10 by 10 or 100 rectangles, and I sample my function at some point on each of those rectangles. In this case, I've just used the point that's closest to the origin of the 4. Once I've sampled it, I use that as my cap. So I cap off the top of the rectangle and I get a bunch of these boxes. Now these are all boxes I can work out the volumes of, and I can add them all up, and I get an estimate for what the volume is underneath the surface. The more rectangles I take, the better my approximation is. So I can ramp this up. I'll just keep taking the number of rectangles more and more and more. In fact, maybe I'll stop at 100 along each of the 2 directions. So this is 10,000 rectangles, and I've sampled the function on each of those rectangles. I've sampled the function and used that as the cap for the top. So if I zoom in close enough, you can see these are all flat tops on them. And I can add all those volumes up, and I get an estimate for the volume underneath my surface. And the idea is that if I let the number of rectangles go to infinity, then I should get the exact value for the volume. So that's the big picture of what we're doing today. So our goal, in order to solve this problem of what is the volume, our goal in this section is to study this problem, so the volume problem, by using a Riemann sum. So that is this idea of chopping up the region into a bunch of little bits, and then in this case using rectangular boxes on each of those bits as an estimate for the volume on that bit, and then adding them all up. That's this notion of a Riemann sum. Then, in the limit, as these number of boxes go to infinity, so then in the limit, we will define the integral. So the integral will be the limit of these Riemann sums, and the integral will give us the exact value of the volume. Then finally, we'll compute the integral using calculus 2 techniques. And by that I mean techniques that we take the antiderivative, we evaluate the endpoint, so we have a way of calculating integrals using antiderivatives from the fundamental theorem of calculus, so we don't have to go ahead and evaluate a limit of a Riemann sum directly. So that's our goal. We've got the volume problem that we're trying to figure out. We're going to estimate it by chopping it up into little bits and using rectangular boxes to estimate the volume. That's going to give rise to this notion of a Riemann sum. We're going to look at taking the limit as the number of boxes go to infinity. That gives us the definition of the integral, which represents the volume. And then we're going to compute said integral by using calculus 2 techniques. So let's get started with this. This is now the ingredients needed to define a double integral. So we're going to start with our function f, and it's going to be defined over a rectangle. In this case, our rectangle is going to be on x, it's between a and b, and then on the y-axis, it's between some c and d. So it's going to look something like this. It's going to be the region that's sort of trapped between all of these things. So that's our region that we're interested in. Maybe I'll highlight it in blue. There's our rectangle. We're going to work out the definition of what the integral is of our function of two variables over this region. And because there's two variables, we refer to this as a double integral. So how are we going to set up the estimates for the volume and then work out what the integral is? Well, we're going to do what we normally do. Whenever we want to solve a problem, we slice it up into a bunch of smaller problems. Anytime we want to solve a problem related to this idea of summing over little bits. So we're going to convert it to a smaller problem. And so here's the picture associated with that, the one on the left. We take our rectangle, we chop it into a bunch of smaller rectangles, and then we just identify what are the subintervals that we get when we chop up the interval on the x-axis and the interval on the y-axis. So if we chop up the interval on the x-axis, it has a full length of b minus a. If I chop it up into n pieces, then the width of one of these pieces, which we're going to call delta x, is the full length, b minus a, but we just split that up into n equal size bits, so it's b minus a over n. In fact, I need to be specific as to how many bits I've split it up into. I think on the previous page I'm going to use m for the number of bits that I split the x-axis into. Well, let's check. Yeah, so we can see for the x-axis we split it up into m equal size bits. And then along the y-axis we're going to split that one up into n equal size bits. So that width there, that's going to be our delta y. We've written it up above, but here's delta y. And that's going to be d minus c over n. And once I know how wide those gaps are, I know immediately what each of those endpoints are going to be, the x1, x2, and so on. x1 is a plus delta x. To get to x2, I have to make two delta x jumps. So there's a delta x jump, and there's another delta x jump. So x2 is a plus two delta x's, and so on. xi is a plus I delta x's, and similarly for the y's. So we've split up our intervals, we've formed these rectangular boxes, and we've got all the ingredients here to put these things together. We've got our delta x and our delta y's defined. We've got our xi's and our yj's defined. And then the ith jth rectangle is the rectangle we get by taking endpoints of our segment on the x-axis to be xi minus 1 to xi, and similarly on the y-axis it will be yj minus 1 to yj. That forms the rectangle. We can sort of see it here in the picture. It's this rectangle right here, the one that's shaded in. So now we've got a description for every rectangle in that picture in terms of the endpoints. And then we collect a bunch of sample points in those rectangles. So one sample point for each rectangle. And those are the gray dots or the white dots that are inside each of those rectangles. And they're just spread all over. It doesn't matter where we pick them, just as long as we pick some sample point in each one. This is analogous to doing things like the left-hand sum or the right-hand sum for functions of a single variable when we were creating those Riemann sums, or the midpoint sum. I mean, we can specify a particular way to choose these sample points, but in general they can be chosen anywhere in the region. What are we going to do with those sample points? Well, that's just where we're going to sample the function height at and use that to cap off this rectangular box. So that's the picture on the right. I've got my Rij rectangle. I pick a sample point inside. I go up, sample my function there, and then once I've sampled my function, I use that as the cap. So I'll zoom in on it. I use this as the cap, so I level it off. And once I've used that as my cap, I form this rectangular box. That rectangular box is going to be what I use to estimate the volume under the surface over that little rectangle. So this would be delta x times delta y, that's the area of the base square, times the height. Well, that's the function value at the sample point. So that's that height. And so I can work out what the volume is. the volume of the ith jth box is given by the height of the ith jth box, which is f of xi j star yi j star multiplied by delta x delta y. This is also what we refer to as delta A. That's the area of this region down here, delta A, which was delta x delta y. And so I've got an expression for the volume of the ith jth box, and then I just add up all of these volumes. And so that's what our definite integral becomes. We take the volume of the ith jth box and we add up over all of them, so we sum j goes from 1 to n, I goes from 1 to m. That's the estimate for any given m and n. That's our estimate for the volume under the surface. If we take the limit as m and n go to infinity, or as the number of boxes go to infinity, then we get the exact value of the volume, which we call the double integral. And so there's our double integral notation. Two integral symbols with the name of the region we're integrating over down below, that's the r, and then our function, and then we've got our dA. dA is analogous to this delta A, which was delta x times delta y, the area of each rectangle. Okay, so we've defined a double integral, and the definition is coming from the fact that we want this to be the volume. So we've defined now the double integral, which gives us the volume. Right now, though, the way we've defined it seems that the only way we can compute it is by setting up this double sum and then taking the limit. But that's not the case. We'll see how we can calculate the value of the double integral using calculus 2 techniques. So before we do that, let's go ahead and see how we can use these ideas to estimate the volume in a particular example. So we go back to our original example of a paraboloid opening down. We've got our region from 0 to 2, 0 to 2. So there's 1, 2, 1, 2. So the region we're interested in is this region here. And it says, find the area above this region below the paraboloid, but use a partition of that rectangular region into 4 equal squares. Okay, so there's our 4 equal squares. We just chop it up like this. We've got our 4 equal squares. Choose our sample point to be the center point of each of those squares. So we choose our sample point to be right in the middle. So that would be 0.5, 1.5, 0.5, and 1.5. And now we're going to use those to get an estimate for the volume. So our volume is going to be, now we just sum over the volumes of each of these rectangular boxes. So we see the base of the box here. The height of the box is going to be the f value, the function value, sampled at the sample point. So what is our height of our first box? Let's say this is box number 1, box number 2, box number 3, and box number 4. Then for the first box, the height would be f of 0.5, 0.5. And then its base area, well, we can work that out. This would be delta x. This would be delta y. And in this case, these are both 1s. So this would be, maybe I'll write it as delta A is equal to delta x times delta y is equal to 1. So that's our area of each of these boxes. So we'd be multiplying by delta A in each of these cases, which is just 1. So we don't really need to include it here because it's just 1, but I will just for completeness. Second box would be f of 1.5, 0.5 times delta A. The next box would be f of 0.5, 1.5 times delta A. And the next box would have volume 1.5, 1.5 times delta A. Delta A's are all 1s, as we've indicated, so that's a 1, that's a 1, that's a 1, and that's a 1. So really we're just summing the function value at each of these points. What is the function value at each of these points? The first point, f of 0.5, 0.5, that has a value of 15.25. f of 1.5, 0.5, that has a value of 13.25. f of 0.5, 1.5, that has a value of 11.25. And f of 1.5, 1.5, that has a value of 9.25. So we can sum up all of these values and we get 49. And so there is our estimate for the volume of the region trapped under the paraboloid above this square in the plane. Now the way we chose our sample points was we chose them to be the midpoints of each of the rectangular boxes. And so what we've done here is we've really done what's called the midpoint rule for double integrals. And the midpoint rule just says the sample points you use are going to be the midpoints of the intervals. And so we've done the midpoint rule for 4 sub-rectangles. The more boxes you use, the better estimate you're going to get. So we've just done it for 4 boxes, and we'll see that this is not too bad. We've actually got a pretty good estimate here. Alright, so we'll end this first part of the lecture with just the properties of the double integral. So our definition of the double integral was in terms of these limits of Riemann sums. What are the properties? The properties are that if you integrate the sum of 2 functions, it's just the sum of their integrals. If you integrate a constant times a function, you can just move the constant out front. So very familiar properties that we had for single integrals, or integrals of a single variable function. The last one, if the function f is always bigger than the function g on that region R, then the integral of f has to be bigger than the integral of g on that region. So again, familiar properties we had, they also hold true for these double integrals. So now we've covered the definition of the double integral, its connection to volume, how to estimate volume using just finite sums. The integral is now the limit of these sums as the number of boxes go to infinity. How do we compute these integrals now? If we want to find the exact value, the exact volume, not just an estimate, but the exact value, how do we find that? Well, we can see how calculus 2 techniques of anti-differentiation and evaluation at the endpoints can come into play. And that's going to be part 2 of this video, and we'll go through a number of examples where we compute the value of a double integral. See you in the next video.